Now, just a real quick reminder that the power rule works for any real number. So if we have x to the n, the derivative of that is n x to the n minus 1, regardless of the number being rational, real, or irrational number. Okay? So some examples of extending all these rules using powers are going to be the following. So first, notice we have the derivative of 9 over x to the 5. Normally, we were doing this, putting the power on top, and now we're saying, oh, okay, so this is 9x to the minus 5. And I still believe that this is the best way to do it, because that means this is 9 times minus 5x to the minus 5 minus 1. That's the derivative. And so this is minus 45 x to the minus 6, right? And that's from just using the relationship between negative powers and the quotient. That is going to be single power, but we can also use quotient rule, right? Now we can use quotient rule for this. And so notice is the derivative of 9 times x to the 5 minus 9, the derivative of x to the 5 over x to the 5 squared. So both cases work. The derivative of 9 is 0. So 0 times x to the 5 minus 9 times 5. And then we get here x to the 4. And then we get here x to the 10. And at the very end, we can see that this is minus 45 x to the 4, x to the 10, which is going to be pretty much equivalent to minus 45 x to the 6 on the bottom, which is exactly the same as what we have here. Okay. Now, the second example is mostly about algebraic tricks. So we have 3t to the 16 minus 4t to the 6. Okay. And so, yes, you could use quotient ruling here. And let's actually do it first that way. This is the derivative of 3t to the 16, right, times t to the 6 minus 3t to the 16 minus 4 times t to the 6 over t to the 6 squared, right? And that's going to be 16 times 3 is going to be 48 t to the 15 times t to the 6 minus, and then we're going to have 3t to the 16 minus 4 times 6t to the 5 over t to the 12. And so that's 48 t to the 21 over here. And this minus 3, well, 3 and 6 is 18. So minus 18 t to the 21, 16 and 5. And plus 4 t to the 5, plus 6 by 4, 24. So 24 t to the 5 over t to the 12. And then notice this is the same power, so I can just say, well, this is 30 t to the 21 plus 4 t to the 5 over t to the 12. And that's it. This is using quotient rule. But we can always find a different ways to approach this. And alternatively, what we can do is we can separate this into things. We can use the denominator and think, well, this is t to the 16 over t to the 6 minus 4 t to the 6. Okay, so that's the derivative of 3t to the 10 minus derivative of 4t to the minus 6. And so as you can see, this is 30 t to the 9 minus or plus 24 t to the minus 7. Okay. Notice that this is very quick to do, not as complicated as doing a quotient rule, and this is exactly the same thing. Take 30t to the 21 over t to the 12, you get 30t to the 9. Take 4t to the 5 over t to the 12, you get 24t to the minus 7. So same thing, same result, but one way is easier to the other. Which one to use? Well, it depends on your criteria and in your ability to check what is the best approach to do this. Finally, just to conclude this section, we have one more example of quotient with a couple powers. So now in this case, we can't really split anything. And the reason why we can split anything is because this time the denominator has a sum. So unfortunately, I can't really split the denominator, and I have to use the derivative of the quotient. So that is derivative of this without taking derivative for this one minus this one and derivative of the second one. Over this square. So this is just made so I can contrast what I just mentioned. So this is 15 over 2, x to the 3 halves. 5 half minus 1 is 3 halves. Now times 2x squared plus 4 minus, and now here 3x to the 5 half. And if I take the derivative of this, this is just going to be 4x. And of course, here you can simplify, you can multiply powers. Remember that you have to use the formula x to the m times x to the s is just the sum of this. Or if you're playing with negatives, then this is what happens. Okay, so that's the type of calculations that we do when we're using quotient rule.